Hello and welcome. Find a comfortable space. Let your shoulders relax, let the noise of the day begin to fade, and just focus on the sound of my voice. Tonight I want to ask you a question. It's a question that has haunted human imagination for generations, a question that lives at the very edge of possibility. Is time travel possible? It sounds like pure fantasy, doesn't it? A wild idea from novels and films. In our everyday lives, our experience of time feels so simple, so absolute. It feels like a rigid, invisible ruler measuring out our existence. The clock on your wall, the watch on your wrist, they seem to tick forward in perfect, unwavering unison with every other clock in the universe. 1 second follows the last, always at the same relentless pace. We are born, we live, and we age. The arrow of time seems to fly in only one direction forward. It's reliable, it's constant, it's the one thing we think we can truly count on. Or is it, what if this feeling, this deep shared intuition of time as a steady universal drumbeat is just an illusion? What if time isn't a rigid iron track, but rather a winding, flowing river capable of changing its speed and its direction? For most of human history, this steady tick-tock was simply a fact of life. But then, just over a century ago, a young patent clerk in Switzerland named Albert Einstein completely shattered that universal clock. In 1905, he introduced his special theory of relativity. It was built on a single radical idea. The speed of light in a vacuum is the ultimate speed limit of the universe. That speed, about 186,000 miles per second, is constant. It doesn't matter if you're standing still or racing in a futuristic rocket. If you measure the speed of light, you will always get the exact same number. This simple rule, which has been proven time and time again, has a bizarre and profound consequence. To keep the speed of light the same for everyone, something else has to change. That something is time itself. Let's try a thought experiment. Imagine two twins. One stays on Earth and the other becomes an astronaut climbing into a spaceship that can travel at incredible speed, say 99% of the speed of light. The astronaut twin travels to a distant star and back a journey that, according to her ship's calendar, takes perhaps 2 years. When she lands back on Earth, however, she finds that her twin is no longer there to greet her. Instead, she is met by her twin's grandchildren. For the astronaut who was moving so quickly, only 2 years passed. But for the twin who stayed on Earth, decades, perhaps a whole lifetime have gone by. This isn't a paradox, it's a proven reality of our universe called time dilation. The faster you move through space, the slower you move through time relative to someone who is moving slower. For the astronaut, her breathing, her thoughts, the very ticking of her watch time itself literally slowed down. This idea shatters one of our most basic concepts, the idea of now. If you and I are moving at different speeds, our now is not the same. When you look up at the Andromeda Galaxy, you are seeing it as it was 2.5 million years ago. But what is happening in Andromeda right now? Einstein's theory tells us that the question itself doesn't really make sense. There is no universal now that blankets the cosmos. But Einstein wasn't finished. 10 years later, in 1915, he gave us his general theory of relativity, and this is where the river of time truly begins to bend. He redefined our understanding of gravity. Gravity, he said, is not some mysterious invisible force pulling objects together. Gravity is a consequence of mass and energy warping the very fabric of reality, a four-dimensional fabric he called space-time. Imagine space-time as a vast, stretched rubber sheet. If you place a heavy object like our sun onto that sheet, it creates a deep dip, a curve. Planets like the Earth aren't being pulled by the sun, they are simply following the curve in space-time created by the sun's mass. We experience this curve as the force of gravity. But here is the critical part, it doesn't just warp space, it warps time. According to Einstein, time itself runs slower in a stronger gravitational field. This isn't just a theory, it is a measurable physical fact. Scientists have taken hyper-accurate atomic clocks, placing one at sea level and another on top of a high mountain. The clock on the mountain, being slightly farther away from the centre of Earth's gravity, ticks just a tiny fraction of a second faster than the clock at sea level. Your head right now is aging microscopically faster than your feet. This effect is of course impossibly small in our daily lives, but what if the gravity was stronger? Let's take that idea to its ultimate conclusion, a black hole. A black hole is an object so massive, so dense that it warps space-time down into an infinitely deep well. As you approach the edge of a black hole, the point of no return called the event horizon, the gravity becomes extreme, and so the effect on time becomes extreme. If you were falling into a black hole, and your friend watched you from a safe distance, a strange and terrifying thing would happen. They would see your clock slow down. As you got closer to the edge, you would appear to move in slow motion, getting slower and slower, until you seemed to freeze entirely red-shifted and frozen at the brink for all eternity. You, however, would feel time passing perfectly normally as you crossed that boundary never to return. If this all sounds like abstract distant science, I promise you it is not. You use this reality every single day. The global positioning system. The GPS in your car or on your phone relies on a network of satellites orbiting high above the Earth. Those satellites are moving very fast, thousands of miles an hour. Because of special relativity time dilation from speed, their internal clocks tick slower than ours on the ground by about 7 microseconds every day. At the same time, those satellites are high up in a much weaker gravitational field than we are. Because of general relativity time dilation from gravity, their clocks tick faster than ours by about 45 microseconds every day. The system must combine these two relativistic effects, correcting for the fact that time is running at a different speed for the satellites than it is for us. If the engineers didn't precisely calculate for both the slowing of time due to speed and the speeding up of time due to weaker gravity, the entire GPS network would fail. Navigation errors would pile up at a rate of several miles per day. The fact that your phone can tell you where to turn is living proof that time is flexible. So let's go back to our starting intuition. That steady, reliable tick-tock of the universe. It was a comforting thought, but it's not the truth. The truth, as it so often is far stranger and far more beautiful. Time is not a rigid, universal metronome, it is a river. It flows, it bends, it meanders around the massive objects of the cosmos. It speeds up and slows down, it is personal. As Einstein proved, every one of us, every planet, every galaxy carries our own personal measure of time. My now is not your now. My river flows at its own pace and so does yours, guided by our speed and by the gravity we feel. And it is in this strange, winding, flexible current that we live our lives. The river of time is not just something we pass through. It is something that passes through us. And it is bending, always bending. We all are. We are all moving through time together on this pale blue dot. We are travelling into the future. It feels constant, doesn't it? Like the steady ticking of a clock, 1 second, then the next second, then the next. We measure our lives by this flow. We are born, we grow older, and we move forward all in a single unbroken line. It feels like a law, 1 second per second, no more, no less. But what if it's not? What if that steady universal flow is just our local experience? What if time is not a single grand universal clock, but something more personal, more flexible? Think of time as a great wide river. All of us are in it, floating along together. We look at the person next to us and we are moving at the same speed. But Einstein's great revolution was to show us that the river doesn't have just one current. There are faster currents and slower currents. And your speed through space, determines which current you are in. When you are moving very fast, you're pushed into a slower current of time. This isn't a fantasy, this isn't a story from a book. Travelling into the future is not science fiction. It is a fundamental, proven fact about the universe we inhabit. The laws of physics don't just allow it, they guarantee it. We have seen it happen, we have measured it. The first time we truly touched this idea, the first time we held proof in our hands was in 1971. It was an experiment that sounds almost too simple. It's called the Haffel-Keating experiment. What they did was take clocks, not just any clocks, but incredibly precise atomic clocks devices that measure time so accurately they might only lose a single second over millions of years. They took 4 of these clocks and put them on commercial airplanes. They just flew them around the world, 2 went eastbound and 2 went westbound. And one clock, the control stayed right there on the ground at the US Naval Observatory. When the planes landed and the travelling clocks were brought back to the laboratory, they were compared to the clock that had stayed home. They no longer agreed. The clocks that flew had experienced time differently. They were out of sync. The clocks that travelled were now lagging behind the clock that stayed still. They were by a tiny, tiny fraction of a second, a few nanoseconds, a few billionths of a second, measurably younger. They had travelled less through time simply because they had moved. Think about that. For a few billionths of a second, those clocks had leaped into the future of the clock that stayed on the ground. It was the first time human beings had ever built a machine, sent it on a journey, and watched it return from the future. This wasn't a fluke. It is happening right now above your head. The astronauts living on the International Space Station orbiting our planet are our first full-time time travellers. They are drifting in zero gravity, watching the world spin below, but they are also moving. They are moving incredibly fast, about 17,000 miles per hour. That's nearly 5 miles every single second. Because they are moving so much faster than we are down here on the surface, their experience of time is different. Their time is running just a little bit slower. For every day they spend in orbit, they age at a few microseconds, a few millionths of a second, less than we do. When an astronaut like Scott Kelly spent nearly a year in space, he came back to Earth having aged just a little bit less than his identical twin brother Mark, who stayed on the ground. He returned to an Earth that was for him about 1/100th of a second in the future. It is a tiny amount, so small we can barely comprehend it. You would never notice it. But it is real, it is measurable, and it proves the principle. The future is accessible. The future is open. The universe isn't a rigid locked box where everyone is forced to march forward in perfect lockstep. Time is personal. My time and your time can be different. The only reason we don't notice it is because in our everyday lives our speeds are just too slow. The car, the train, even the jet plane, they are all just crawling compared to the true speed limit of the universe. The real leap, the true journey happens when you get close to that ultimate speed, the speed of light. 186,000 miles per second. We haven't built a ship that can do this, not yet. The energy required is staggering far beyond anything we can currently imagine. But we can imagine the journey. We know what the laws of physics say would happen. Let's imagine that ship. A vessel of light and energy capable of pushing itself faster and faster until it is moving at, say, 99% of the speed of light. For the crew inside, everything would feel normal. They would eat, sleep, and talk. A minute would feel like a minute. An hour would feel like an hour. Their hearts would beat at a normal rate. But from our perspective here on Earth, we would see their clocks ticking at a crawl. At 99% of the speed of light, for every 1 year that passed for the crew on that ship 7 years, would pass on Earth. They could take a 3-year journey by their calendar and return to an Earth that was 21 years older. But what if we go faster? What if we could reach 99.99% of the speed of light? The effects become astonishing. At that speed, 1 year on the ship would equal 70 years on Earth. Let's go even further. 99.9999%. Now for every 1 year on the ship, 7,000 years pass on Earth. Imagine taking that journey. You board this ship, you say goodbye to everyone you know, you travel for just 1 year perhaps to a nearby star and back. You feel yourself age 1 year. Your hair is a little greyer, you've celebrated 1 birthday. But when you return, when you look for your home, it is gone. 7,000 years of human history have passed. The continents may have shifted. The languages, the cities, the people, all of it would be an ancient forgotten past. You would be a visitor, a relic in a world you could not possibly recognize. You have successfully traveled to the future. But this of course brings up a famous confusing question. It's the one everyone asks. It's called the twin paradox. Imagine 2 identical twins, one stays on Earth, the other gets in that incredibly fast ship. The paradox is this. From the perspective of the twin on Earth, the ship is moving, so the astronaut twin's clock must be running slow. But from the perspective of the astronaut on the ship, it's Earth that is moving away from him at high speed. So wouldn't he see the Earthbound twin's clock as running slow, who is really aging less? It's a wonderful question, and the answer is what makes time travel possible. The situation is not symmetrical. There is a fundamental difference between the 2 twins. The twin on Earth stays in one place. She just waits. She doesn't speed up or slow down. But the astronaut twin, his journey is violent. He has to accelerate to an incredible speed. He has to slam on the brakes to stop. He has to turn around, which is another form of acceleration. And then he has to accelerate again to come home and decelerate again to land. It is this acceleration, this change in motion that breaks the symmetry. The universe knows who went on the journey. The laws of physics unambiguously state that the person who undergoes the acceleration is the one who will experience less time. When the ship lands, there is no paradox. The twin on Earth will be old or perhaps gone for centuries. The twin who travelled will still be young. He has paid for his ticket to the future with the only currency that matters, time. He has traded his now for humanity's later. It's a staggering thought. The universe has written these instructions for us. The rules for this grand journey are not hidden in some mystical realm. They are here in the mathematics of relativity written down over a century ago. It's not magic, it's physics. We are living in a cosmos that has woven into its very fabric the possibility of leaping forward, of seeing what we will become. The challenge is not one of theory. We know how. The challenge is one of engineering. It is a challenge of energy. The universe, it seems, has built a vast ocean with countless currents of time. We have spent our whole existence on one small island, believing our beach was the only reality. Now we've built tiny rafts, the airplanes, the space stations, and we've dipped our toes in a different current just for a moment. We've proven the ocean is real. We just haven't built the ship yet. We haven't learned to raise the sails to catch that cosmic wind. But the instructions are here. The destination is waiting. The future is open. When we talk about time travel, moving into the future is the easy part of such. As Albert Einstein showed, it is physically possible. All you have to do is move very, very fast, close to the speed of light, and time will slow down for you relative to everyone else. When you stop, you will have stepped out into their future. It is a one-way trip, but the laws of physics allow it. The past, however, is a different story. It is not a destination, it is a memory. It is finished. And trying to go back into it opens up a universe of problems. The single greatest barrier to travelling backward in time is not technology, but logic. It is the simple, unbreakable rule of causality, the law of cause and effect. Everything that happens, happens for a reason. An effect can never come before its cause. You must turn on a light switch, cause before the light turns on effect. You must be born, cause before you can live your life effect. The universe is built on this chain of events, one linking to the next in a single unbroken line. Backward time travel threatens to take a pair of scissors to this chain. This is where the deep insecurity about the past comes from. If you can go back and alter a cause, what happens to the effect that you already know existed? This problem is most famously illustrated by the grandfather paradox. It is a logical loop that on its surface seems to have no solution. Imagine a scientist builds a time machine. He decides to travel back 50 years to find his own grandfather, back when his grandfather was a young single man. For some reason, perhaps an accident, or perhaps the scientist has dark intentions, the time traveller causes the death of his young grandfather. Now the paradox begins. If the grandfather dies before he meets the scientist's grandmother, then one of the scientist's parents is never born. If that parent is never born, then the scientist himself is never born. But if the scientist is never born, he cannot grow up to build a time machine. And if he never builds a time machine, he cannot go back in time to kill his grandfather. But if he doesn't go back in time, then the grandfather lives, meets the grandmother, and has a child. That child grows up to have the scientist who does build the time machine and does go back. We are now in an impossible loop. Both the scientist exists and the scientist does not exist are true at the same time. Reality cannot support such a contradiction. It is a logical short circuit. This paradox suggests that travelling to the past in a way that allows you to change it is simply impossible. Physicists and philosophers, however, have thought of a few ways the universe might protect itself from this. There are two main theoretical solutions. The first solution is called the Novikov self-consistency principle. This principle is in many ways the simplest and most elegant solution. It states that the past is fixed, absolute, and cannot be changed. It is not that you shouldn't change the past, it is that you are physically incapable of changing it. Let's replay the grandfather paradox with this rule in place. The scientist goes back in time with the goal of killing his grandfather. He finds him, he aims his weapon, and then he slips on a banana peel, or the weapon jams, or a bird flies in the way at the last second. Or perhaps as he looks at his young grandfather, he simply has a change of heart and finds he cannot do it. No matter what he tries to do, the outcome is always the same, the grandfather survives. This theory goes even deeper. It suggests that if you travel to the past, you are not an outside force, you are and always were a part of that past. Your actions were already factored into the history that you know. For example, if you went back to see a famous battle, you might discover that the mysterious soldier mentioned in the history books, the one who saved the general, was actually you. You were not changing history, you were creating the history you always knew. In this model, you have no free will to change things. You are simply an actor, playing a part in a play that has already been written. The second solution is more dramatic and comes from the strange world of quantum physics. This is the idea of parallel worlds or the many worlds interpretation. This theory says yes, you can change the past, but the moment you do, you break reality. When the scientist goes back and successfully kills his grandfather, he does not destroy himself. Instead, he has created a new timeline, a fork in the road. At that very instant, the universe splits in two. Timeline A is the original one he came from. In this timeline, the scientist built a machine, travelled back, and then simply vanished. He never returned. His grandfather lived, his parent was born, and he was born. That reality continues unchanged. Timeline B is the new one he just created. In this timeline, the grandfather is dead. The scientist's parent will never be born, and the scientist himself will never be born in this universe. The time traveller is now stranded. He is a paradox, an orphan of time living in a reality that he does not belong to. He can never go home to his original timeline, because the past of the world he is in no longer matches his own personal history. This solution avoids the logical loop by creating a new separate universe to contain the paradox. Beyond paradoxes, there is an even more fundamental question. Why does time move in one direction at all? Why do we remember the past but not the future? This is known as the arrow of time. Most of the laws of physics, like gravity, do not care about the direction of time. A video of a planet orbiting a star would look perfectly normal if you played it backward. But there is one law that defines the direction, the second law of thermodynamics. This law deals with entropy. Entropy is simply a scientific word for disorder or randomness. The second law states that in any closed system like the universe itself, the total amount of entropy of disorder will always increase. It never ever goes down. This law is the engine that drives time forward. Think of an unbroken egg. It is a system of low entropy. It is highly ordered. The yolk is in the center, the white is around it, and the shell holds it all together. If you drop the egg, it shatters. It becomes a system of high entropy. The yolk and white mix, the shell fragments are scattered. It is disordered. You will wait forever, but you will never see the shattered egg on the floor spontaneously pull itself back together, reform the shell, and fly back up into your hand. That would be a massive decrease in disorder, which the universe forbids. Think of ice cubes melting in a glass. The cube is an ordered crystal. The puddle it becomes is disordered liquid. The puddle will not spontaneously refreeze into a perfect cube. Time only moves in the direction of more disorder. The universe itself began in a state of very low entropy, the Big Bang, and has been expanding and becoming more disordered ever since. Our brains work this way too. We form memories by creating connections which uses energy and increases the total entropy of the universe. We can remember the past, the direction of increased entropy, but we cannot remember the future because it has not happened yet. This gives us a final contemplative thought. Human beings are defined by a deep, powerful longing to fix our mistakes. We all have moments we wish we could undo, words we wish we could take back, tragedies we wish we could prevent. This desire to edit our lives is a core part of who we are, but the universe seems to have locked the door to the past. The laws of causality, represented by the paradoxes and the irreversible march of entropy, have sealed it shut. To break those laws would be to unravel the very fabric of cause and effect that allowed us to exist in the first place. Perhaps that is why the past is locked. It is protected not from us, but for us. It must remain finished so that the present can have meaning, and so the future can still be written. Let's return to that beautiful heavy fabric of space-time we've been picturing. We've talked about how it bends, how it curves, how it dictates the way everything moves. We know that gravity, the presence of mass, can create a dent, a curve, a gravity well that pulls things in. But what if the universe could do more? What if it could fold? Imagine you're a tiny microscopic ant on a vast sheet of paper. You stand at one corner and your destination is the corner diagonally opposite. To walk there, you must trace a long, long path across the entire sheet. It will take you hours. But what if a giant hand reached down and folded that paper in half? Suddenly, the point where you stand is touching the point where you want to go. You could just step across. This is the simple, breathtaking idea behind what we call a wormhole. It's a theoretical passage through space-time that could create a shortcut for long journeys across the universe. This isn't science fiction. It emerges directly from the same equations of general relativity that describe black holes. This theoretical shortcut was first explored mathematically by Albert Einstein and his colleague Nathan Rosen. In the mathematics, it appeared as a bridge, a perfect tunnel connecting two separate regions of space-time. We call this the Einstein-Rosen bridge. It is in theory the ultimate cosmic shortcut. Not travelling through space but under it, bypassing it, taking the hidden path. You could in this fantasy connect 2 points in the same galaxy or 2 points in entirely different galaxies billions of light years apart. The journey wouldn't feel like a journey at all. You wouldn't be racing a beam of light, you would simply be stepping out of a door in your home and instantly arriving in a city across the world. You would enter one mouth of the wormhole and emerge from the other, potentially on the other side of the known universe. But the true wonder of this idea, the part that truly challenges our understanding of reality, isn't just about conquering distance, it's about conquering time. A wormhole in its simplest form connects two locations, but what if we could make it connect 2 times? Let's imagine we have one of these stable wormholes. It has 2 mouths. Let's call them door A and door B. They both exist in the same now. You step into A, you come out of B instantly. You step into B, you come out of A instantly. Just a simple cosmic doorway. Now what if we take door B and put it on a truly advanced spaceship? We send that spaceship on a very, very long journey at nearly the speed of light, say 99.9% of light speed. It travels for what we back on Earth measure as 100 years. But as we learned from Einstein, extreme speed causes time dilation. Time for door B slows down. The clock at door B, which is travelling fast, ticks much, much slower than the clock for door A, which stayed comfortably at home. When the ship returns and parks door B next to door A profound difference has occurred. While door A has aged 100 years, the fast-moving door B has aged perhaps only 1 year. Door A is in the year 2100, door B is in the year 2001, but the tunnel, the bridge between them, is still intact. Now what happens if you in the year 2100 step into door A? You will emerge from door B, but door B exists in the year 2001. You haven't just travelled through space, you have travelled into the past. And what if someone in 2001 steps into door B? They will emerge from door A in the year 2100. They have travelled into the future. You have in theory built a time machine. So why aren't we doing this? Why aren't time travellers visiting us right now, stepping out of strange shimmering doorways? The universe, it seems, places profound obstacles in our path. The first obstacle is stability. These bridges, as described by Einstein's equations alone, are tragically fleeting. They are not pathways, they are flashes. The moment they form, they pinch off and collapse, and so fast in fact that not even a single particle of light would have time to cross. Any traveller attempting the journey would be annihilated in the collapsing singularity. To hold the tunnel open, to prop the doorway open so something could actually pass through, you would need something truly strange. You would need exotic matter. This isn't matter like the chair you're sitting on or the star shining in the sky. This would have to be matter with negative mass or negative energy. Something that possesses a kind of anti-gravity, something that pushes space-time apart instead of pulling it together. We have never observed such a thing. It lives only in our equations, a mathematical requirement. Without it, the bridge collapses. And this leads us to the second deeper obstacle, the paradox. We find ourselves once again standing before that great logical abyss, the grandfather paradox. If you can untravel to the past, you can change it. You could go back and prevent your own birth. But if you prevent your birth, how could you have existed in the first place to build the time machine and make the journey? It's a loop that eats itself, a question that has no answer. Does the universe have a protection mechanism? A cosmic censor that forbids such paradoxes from ever forming? Perhaps the very exotic matter we need to build the machine is impossible to create for this very reason. Perhaps the laws of physics themselves will always intervene, slamming the door shut before we can break the fundamental logic of cause and effect. Or perhaps, as some theories suggest, does stepping into the past simply create a new parallel timeline, leaving your own untouched? For now, the wormhole remains a ghost. It is a beautiful, haunting whisper in the mathematics. It's a hidden tunnel drawn on the blueprints of the cosmos, but with no entrance we can find. It is a bridge waiting to be built, but with materials that may not even exist. It is one of the most profound what-ifs in all of science. It reminds us that the fabric of reality is perhaps far more intricate, far more magical than our senses can perceive, that there may be folds and tunnels and secret passages woven right into the world we see. And as you drift off to sleep, perhaps you can picture it, a quiet fold in the darkness, a silent doorway waiting. To solve the first great hurdle, the fact that a wormhole would slam shut instantly, we need something that breaks all the rules we know. We need a substance that can prop the tunnel open, pushing outward against the universe's tendency to crush it flat. This theoretical, almost magical substance is known as exotic matter. To understand what makes it so exotic, we first have to think about normal matter. Everything you have ever seen or touched, from a feather to a star, is normal matter. And normal matter has one defining rule: it has positive mass, and therefore it creates gravity. It pulls things toward it. In Einstein's view, normal matter tells space-time how to bend, creating a dip or a well, like a bowling ball placed on a trampoline. Other things then fall into that well. Exotic matter would be the exact opposite. It would have negative mass. This concept is so bizarre it's hard to even imagine. If you had a ball of exotic matter, it wouldn't create a dip in space-time. It would create a hill. It wouldn't pull things toward it, it would actively push them away. It would be a source of anti-gravity. If you tried to push it with your hand, some theories say it might move toward your hand instead of away from it. This is precisely what we need for our wormhole. We could take this exotic matter and line the throat of the tunnel with it. Its repulsive, pushing force would act like a cosmic support beam, forcing the tunnel to stay open. It would fight against the crushing force of gravity and stabilize the bridge, allowing a traveller to pass through without being annihilated. Without this anti-gravity scaffolding, a wormhole is just a theoretical dead end, a bridge that vanishes the moment you try to set foot on it. So the next logical question is, does this stuff even exist, or is it just a convenient invention, a cheat code that physicists put into their equations to make the math work? The shocking answer is it might exist. We have a tiny, fragile, laboratory-confirmed piece of evidence. This evidence is called the Casimir effect. To understand this effect, you must first accept a very strange idea from quantum physics. Empty space is not empty at all. A vacuum which we think of as pure nothingness is actually a bubbling, chaotic soup of virtual particles. Tiny particles of matter and antimatter are constantly popping into existence and then crashing into each other, disappearing in a tiny flash of energy. This chaos happens everywhere all the time. It is the background energy of the universe. The Casimir effect, first predicted in 1948 and measured decades later, shows what happens when you disturb this vacuum energy. If you take two perfectly smooth uncharged metal plates and place them incredibly close together, less than the width of a human hair, something strange occurs. Outside the plates, the full chaotic soup of virtual particles is pushing on them. But between the plates, the space is so small that only certain virtual particles, specifically those with very short wavelengths, can fit. Many of the particles are crowded out. The result is that there is more pressure pushing the plates from the outside than there is pushing them apart from the inside, and so the plates are forced together by the empty space around them. What does this have to do with exotic matter? The region between the plates, which has been emptied of some of its normal vacuum energy, now has less energy than the vacuum around it. It has become a tiny, localized region of negative energy. It is real physical proof that negative energy, the key ingredient for exotic matter, is allowed by the laws of physics. This is the good news. Now the bad news. The amount of negative energy produced by the Casimir effect is microscopic. It is unbelievably small, barely enough to measure with our most sensitive instruments, let alone prop open a gateway to another galaxy. To stabilize a wormhole just 1 meter wide, big enough for a person, it's estimated you would need an amount of exotic matter equivalent to the entire mass of the planet Jupiter, but in negative form. We have absolutely no idea how to create or gather this much. The Casimir effect is a quantum-scale curiosity. It is not by any stretch an engineering blueprint. We can't bottle the space between the plates and build a spaceship out of it. Even if we could, and a far more serious problem awaits us: control and stability. Let's pretend we have our Jupiter mass of negative energy matter. We now have to shape it perfectly and use it to line our tunnel. The moment we try to send something through even a single particle of light, all hell would break loose. The interaction between the normal matter of our spaceship and the exotic matter of the wormhole would be violently unstable. The entrance to the wormhole would act like a terrible cosmic amplifier. As your ship approaches, the light and energy from it would enter the tunnel, loop around, and gain energy with each pass. This would create a feedback loop. The energy would build up, shifting higher and higher on the blue end of the spectrum, becoming infinitely powerful in an instant. The result? A tremendous explosion of radiation. The wormhole would violently destroy itself and anything or anyone attempting to use it in a flash of light. It's like a doorway that is rigged to explode the second a security camera sees you approaching. This quantum instability suggests that even if we could build the bridge, the very act of crossing it would be impossible. Finally, there is the most fundamental obstacle of all. Physics, it seems, has a built-in defense mechanism against these kinds of shortcuts. These rules are known as the quantum inequalities. These are a set of theoretical limits that seem to govern negative energy. In simple terms, the universe might let you borrow some negative energy, but it's a very short-term loan, and the interest rate is impossible. The quantum inequalities thus state that while you can create a region of negative energy like the Casimir effect, it must be immediately followed or balanced by a much larger burst of positive energy. You can dig a hole negative energy, but you must create a pile of dirt positive energy right next to it. You can never just have the hole. Crucially, the rule says that the more negative energy you try to create, the shorter the amount of time you're allowed to have it. To keep a wormhole stable, you don't need a quick flicker of negative energy. You need a massive, stable, permanent field of it. The quantum inequalities seem to forbid this outright. They declare that any attempt to build a large, stable structure out of exotic matter is fundamentally impossible. The universe will always demand payment, forcing you to flood your negative energy hole with positive energy, causing the whole structure to collapse. This is where we stand. The pathway to the stars requires a substance that we cannot find in quantities we cannot imagine, which we cannot control, and which the fundamental laws of physics seem to forbid us from ever using. And yet the idea persists. It is, as one physicist said, the kind of fiction that the laws of physics seem to allow. The equations on paper, Einstein's equations, have a blank spot waiting. They tell us that if you could find this matter, the universe would bend to your will. The door is still there. The math says it can exist. It just seems to be locked by every law we know. But the key, perhaps, is just a new discovery, a new law of physics waiting to be found. In our journey so far, we've imagined punching holes in the fabric of space, creating shortcuts we called wormholes. We've wondered if we could ever break the ultimate speed limit to travel faster than light. But there is another possibility, one that is perhaps even more unsettling. What if you don't need a tunnel? What if you don't need impossible speed? What if the universe itself is built in such a way that time simply loops? Imagine the fabric of space-time not as a flat sheet, but as a complex, twisted and warped piece of geometry. What if the universe itself could be structured not like a straight road, but like a roundabout, a path, where if you just keep moving forward, you eventually and naturally return to your own past? This isn't science fiction. This is a concept in physics known as a closed time-like curve. Let's break that down. Curve means it's a path through space-time. Time-like is the crucial part. It means it's a path that normal matter, you mere spaceship, can actually travel without ever breaking the speed of light. And closed, that means it's a loop, a path that begins and ends at the same point in space-time. This idea is deeply disturbing to physicists, but it didn't come from a fantasy novel. It came from one of the most brilliant minds of the 20th century, a man who was Albert Einstein's closest friend at Princeton, Kurt Gödel. In 1949, Gödel did something remarkable. He wanted to test the limits of his friend's new theory of general relativity, and he found a solution to Einstein's own equations that described a universe. But this universe was strange. It was a universe that was rotating. In this Gödel universe, the entire cosmos, all the galaxies and dust was spinning, and this universal rotation did something profound to space-time. It dragged the fabric of reality along with it, twisting the paths of light and matter. Gödel proved mathematically that in this kind of universe you could get in a spaceship and take a very, very long journey. You would fly in a vast circle, and when you returned to your home planet, you would arrive before you had ever left. You wouldn't have broken any local laws. Your ship's clock would have ticked forward normally. You would have just been following the natural curve of space and time, a curve that had been so twisted by the universe's rotation that it looped back on itself. Now we are fairly certain we do not live in a Gödel universe. Our observations show the universe is expanding, not rotating. But that wasn't the point. Gödel's discovery was a mathematical bombshell. It proved that Einstein's equations, our best description of gravity and the cosmos, did not forbid time travel. The laws of physics, as we understood them, allowed for the existence of closed time-like curves. If the universe itself isn't rotating, could we make something rotate to achieve the same effect? This led to other more engineered models. The most famous is the Tipler cylinder, proposed by physicist Frank Tipler. Imagine a cylinder, but not just any cylinder. Imagine one that is astronomically long, perhaps infinitely long, and it's dense, incredibly dense, packed with the mass of stars. And now imagine this infinite cylinder spinning on its axis faster and faster until its edge is moving at nearly the speed of light. This object would be one of the most extreme things in the cosmos. It wouldn't just spin in space, it would spin space itself. It would create an inescapable whirlpool in the fabric of space-time, a vortex of frame dragging. According to Tipler's calculations, if you flew your spaceship in a very precise spiral path around this spinning cylinder, you would be caught in that space-time current. You would be following a path, a closed time-like curve. You could navigate your way back to any point in your own history. And again, the most startling part, you don't need to go faster than light. You're simply a ship sailing on a river. But this river, the current of space-time, is flowing in a circle. You're always moving forward relative to the water around you, but the water itself carries you back to where you began. This all sounds so possible. So why isn't it happening? Why aren't we besieged by tourists from the future? This brings us back to the great shadows that hang over these ideas. The paradoxes, the grandfather paradox. If you can go back, you can change the past. If you change the past, you destroy the present. It's a crack in the very logic of cause and effect. For many physicists, this is simply too much. It suggests a fundamental flaw in our thinking. The great Stephen Hawking, for one, found the idea of time loops abhorrent. He didn't like that the universe could allow for such logical chaos. So he proposed an idea, a principle he hoped was true, which he called the chronology protection conjecture. It's a beautiful name for a simple idea the universe protects its own history. Hawking suggested that the laws of physics themselves must have a built-in security system, that the moment you try to create one of these time loops, nature itself conspires to stop you. How? Perhaps at the instant you spin up a tippler cylinder, or the moment a wormhole's mouth gets old enough to allow travel into the past, a feedback loop begins. Quantum mechanics tells us that empty space is filled with a sea of virtual particles popping in and out of existence. Hawking proposed that these particles would pour into the time loop circle around and gain infinite energy. They would create a surge of radiation so powerful, so violent it would destroy the machine or the wormhole or the cylinder in a blinding flash. The universe in essence self-destructs the path before any paradox can be created. This conjecture is a hope, not a proven law, but it feels right to many. It suggests that while the equations might permit these strange geometries, the physical reality of our universe, the one built on quantum rules, forbids them. So where does that leave us? We are left with this haunting image, this Mobius strip of experience. A Mobius strip, as you know, is a loop of paper with a single twist. It only has one side. If you trace your finger along its surface, you will travel the entire loop and end up right where you started, but upside down. What if causality is like that? Not a straight line from past to future, but a single continuous self-referential loop. What if the universe is a story that in some profound way writes itself? It's a strange contemplative thought, that the river of time which we feel flowing so steadily past us might in the unseen depths of cosmic geometry be curling back upon itself. This leads us to one of the most bizarre, fascinating and perhaps terrifying solutions to the time travel paradox, the quantum solution. All the paradoxes we've discussed, especially the grandfather paradox, are built on one simple assumption that there is only one timeline. They assume time is a single fragile thread that can be snapped or tangled. But what if that assumption is wrong? What if you travel to the past and stop your grandfather from meeting your grandmother, and nothing happens to you? What if you don't change your past, but instead you create a new one? This is the core idea of the many worlds interpretation, or MWI, a concept born from the strange rules of quantum mechanics. This interpretation was first proposed seriously by a physicist named Hugh Everett III. He was trying to solve a deep mystery at the heart of physics. In the quantum world, before you measure it, a particle like an electron doesn't have a definite position. It exists in a superposition, a fuzzy cloud of all its possible locations at once. The old standard Copenhagen interpretation said that the moment you look at it, this cloud of possibilities collapses and the particle chooses one single spot to be. Everett asked a brilliant question. What's so special about us looking? Why should a measurement cause the universe to make a choice? He proposed a radical alternative. He said the universe never chooses. Instead, every single time a quantum event could go one way or another, the entire universe splits in two. Think about that. A radioactive atom has a 50-50 chance of decaying in 1 minute. According to many worlds, after that minute, there are now two universes. In one, the atom decayed. In the other, it did not. This isn't just a thought experiment. Everett proposed that this happens for every quantum choice everywhere all the time. When a photon hits a piece of glass and has a chance to be reflected or pass through, the universe splits. In one reality it reflects, in another it passes through. And this doesn't just apply to atoms, it applies to us. When you stand at a crossroads and choose to go left, you have just participated in a branching. A new universe is instantly created, or branched off, where another version of you equally real chose to go right. This means there is an infinite, ever-growing, ever-branching tree of parallel realities. There is a universe where you took that job, a universe where you didn't, a universe where you said the thing you wish you had said, and a universe where the dinosaurs were never wiped out. Every possibility is real. Now let's apply this staggering idea to time travel. When you build your time machine and travel to the past, you are not traveling up the single thread of your own history. According to this theory, that is impossible. Instead, your arrival in the past is itself a quantum event that forces a split. The moment you step out of your machine, you have created a new branch of reality, a parallel timeline. Let's call your home timeline Timeline A. In Timeline A, you were born, you built a time machine, and then you vanished. Now you arrive in the year 50, but this is Timeline B. It was identical to your past right up until the exact second you appeared. Here in Timeline B, there is no paradox. You are free to do anything. You can find your young grandfather and tell him not to enlist. He listens to you, he never meets your grandmother, they never have your mother, you do not fade from existence. Why? Because you are not from this timeline. Your mother was born in timeline A. Your grandmother and grandfather did meet in timeline A. You are just a visitor here, a refugee from another branch of reality. You have successfully prevented the birth of the timeline B version of yourself, but your own history from timeline A remains completely intact, locked safely away in its own parallel universe. The contradiction is gone. This seems like the perfect solution, but it comes with two enormous problems. The first problem is scientific. These branches cannot communicate with each other. The reason we don't feel the universe splitting every second is because of a process called quantum decoherence. Think of two identical ripples in a pond moving in perfect sync. This is the superposition. The moment a tiny speck of dust or a gust of wind, the environment hits them, they are knocked out of sync. They decohere and become two separate independent ripples that will never again act as one. The same thing happens to the universe. The split worlds are coherent for only an impossibly small fraction of a second before they interact with their environment. Once they decohere, they are sealed off from each other forever. They can no longer interact, communicate, or see each other in any way. This is the barrier. Even if you could travel to the past and create timeline B, there is no known way to jump back to timeline A. The connection is permanently severed. This leads to the second, much more human and philosophical problem. Is this really time travel or is it exile? If you travel back to save someone you loved, you might succeed. You could go to timeline B and prevent the accident. You could live out the rest of your life with them in this new altered world you have created. But the entire time you would know the truth. You haven't fixed your past, you have abandoned it. Back in your home timeline. The person you loved is still gone. Your friends and family in that timeline are now grieving for two people, the person who died and you, the person who built a time machine and simply vanished forever. You can never go home. You are a permanent refugee, an alien in a world that looks like yours but isn't. You have traded your entire universe for this new one. You have not changed your past. You have simply run away to a different one. This is a solution born of quantum mechanics, but it is a solution with a terrible, tragic cost. So perhaps we need a new image for time. We are taught to think of time as a single straight line, like a piece of string. The past is fixed, the future is unwritten. But maybe this is wrong. Maybe time is not a string at all. Maybe time is a vast field of outcomes. Imagine a giant sprawling garden where every possible event is a seed. As reality moves forward, an infinite number of these seeds sprout, growing into a dense, tangled, branching forest of what-ifs. We in our single consciousness only ever get to walk one path through this forest. We see our path as the only path. But the many worlds interpretation suggests that all the paths are real, and the time traveler is not someone who can bend their own path, but merely someone who has found a way to jump from their path onto another far distant one, never to return. In the quiet, velvet dark of the cosmos, the most powerful tool we have is not a telescope. It is not a spaceship. It is the human mind asking the simple, profound question, what if? This is the power of the thought experiment. It's an experiment conducted entirely within the laboratory of the imagination. It's how Einstein raced a beam of light and discovered relativity. It's how we can fall into a black hole and return all without leaving our world. And in the late 20th century, this tool was used by two of the greatest minds in physics to have a great debate, a friendly clash of titans over one of the most forbidden and fascinating ideas of all time travel. This was the debate between Kip Thorne and Stephen Hawking. It was not a debate about blueprints or building materials, it was a deep fundamental disagreement about the laws of nature themselves. Does the universe allow us to break the chain of cause and effect? Or does it, in its very structure, protect its own history? On one side you had Kip Thorne, a master of Einstein's equations of general relativity, a man who believes in the power of mathematics. For Thorne, if the equations show that something is possible, we must take that possibility seriously, no matter how wild it seems. His journey into this started, as these things sometimes do with science fiction. His friend, the great astronomer Carl Sagan, was writing his novel Contact, and he wanted a scientifically plausible way for his hero to travel across the galaxy. He proposed a wormhole, a tunnel through space-time. Sagan, being a meticulous scientist, called his friend Thorne and asked, "Is this real or am I making it up?" Thorne took the question seriously. He and his students went to the blackboard. They dove deep into the complex mathematics of general relativity, and what they found astonished them. The math worked. The equations did not forbid a stable, traversable wormhole, but they didn't stop there. They realized that a wormhole was more than just a shortcut. If you could create one, you could in theory turn it into a time machine. There was one catch. A huge universe-sized catch. To hold this wormhole open, to stop it from collapsing on itself, you would need a new undiscovered type of matter. He called it exotic matter. This wasn't just something rare. It was something that would have to have properties that sound like fantasy. It would need to have negative mass or negative energy. It would need to weigh less than nothing. If you tried to push it, it would move towards your hand. We have never seen this substance. We have no idea if it can exist. But Thorne, as a theorist, said that isn't the point. The point is that the laws of physics don't forbid it. His conclusion was one of mathematical optimism. The universe, according to its own rulebook, seems to leave the door open for time travel if you can find this one magical ingredient. On the other side of this debate was Stephen Hawking. Hawking heard Thorne's arguments, he looked at his math, and he agreed. The math was correct, but his conclusion was the exact opposite. His was a philosophical objection. Hawking felt on a deep intuitive level that this simply could not be allowed to happen. He believed the universe must have a built-in safety net. It must protect chronology. Why? Because of the paradoxes. The most famous, of course, is the grandfather paradox. What if you built a time machine, went back, and by terrible accident prevented your own grandfather from meeting your grandmother? You would never be born. But if you were never born, you could never have built the time machine to go back in the first place. It's a logical contradiction. It's a crack in the very foundation of cause and effect. Hawking said the universe would not tolerate this. He believed that the laws of physics themselves would conspire to prevent it. He proposed an idea with a wonderfully dramatic name, the chronology protection conjecture. This conjecture states that the laws of physics will always prevent a time machine from being created. But how? Hawking turned to the other great pillar of physics, quantum mechanics, the strange rules of the very, very small. He suggested that the moment you tried to use a time machine, the universe would destroy it. He imagined a powerful feedback loop. Think of the piercing shrieks when a microphone gets too close to its own speaker. The sound goes and gets amplified, comes out and feeds back in again, escalating to an unbearable howl in a fraction of a second. Hawking argued the same thing would happen at the mouth of a time-travelling wormhole. A single particle of light, a photon, might loop back through time. It would emerge and re-enter the loop joined by itself. And again, billions upon billions of times in an instant. This loop of energy would become a runaway reaction, a storm of infinite energy that would blast the wormhole apart, destroying it completely before anyone or anything could ever pass through. The universe, Hawking said, would slam the door shut. He was so convinced of this, so sure that time travel to the past was impossible, that he performed a famous and slightly whimsical experiment of his own. He held a party. At his university in Cambridge, he prepared a beautiful reception. There were balloons, there was champagne on ice, there were snacks. He sat in the room and he waited. But the party was for a very specific set of guest time travellers from the future. The trick was he didn't send out the invitations until after the party was over. He printed beautiful, elegant invitations which read, "You are cordially invited to a reception for time travellers to be held at the University of Cambridge. The party will be on June 28, 2009. The invitation included the precise coordinates of the room in both space and time. His logic was simple. If time travel was ever invented in 100 years or 1,000 or 1,000,000, someone might find that invitation. They could power up their machine, set the coordinates, and pop in for a visit. He sat, he waited, the clock ticked. No one came. The champagne remained uncorked. The balloons hung motionlessly into the silent room. I have experimental evidence, he later joked, that time travel is not possible. And so this debate leaves us with this beautiful contemplative image. Picture it. Two of the greatest minds of our time, they are looking at the exact same set of equations, the very laws that govern the cosmos. They both nod. They both agree on what the mathematics says. And yet, when they look up from the page, they see two completely opposite philosophical conclusions. Thorne looks at the equations and sees a universe of possibility, a universe with loopholes, with hidden doors, a place that is playful and strange, inviting us to be clever enough to find the keys. Hawking looks at those same equations and sees a universe of order, a universe that is rational, logical, and safe, a universe that protects its own story from the chaos of paradox. Who is right? We still don't know, the debate is unresolved, the equations are silent on the final answer, and perhaps that is the most beautiful part of all. The fact that we don't know. It shows us the very edge of our understanding that line where the solid ground of a laboratory ends and the vast open ocean of the what-if begins. As you rest, as you drift, you can ask yourself, which universe do you believe in? The one of infinite strange possibility, or the one of the perfect protected order? For more than 100 years, ever since Albert Einstein first showed us that time is not a rigid universal clock but a flexible fabric woven into space, we have been haunted by a possibility. If time can be bent, stretched, and slowed down, can it also be reversed? If we can travel through space, can we also travel back through time? Scientists, philosophers, and storytellers have explored this profound question, but when we stop theorizing and start looking for an answer in the real world, we are met with a profound and unbroken silence. After a century of searching after countless experiments and observations, we have found not one single piece of experimental evidence that travelling backward in time is possible. This absence is perhaps the most important clue we have. It is important to be clear about what we have seen because it is often confused with true time travel. We have absolutely confirmed that time is relative. This is called time dilation, and it is a real measurable phenomenon that is part of our daily lives. The global positioning system GPS in our phones, for example, must account for time dilation every second. According to Einstein's theories, time moves at different speeds depending on gravity and motion. The GPS satellites are high above the Earth where gravity is slightly weaker. This causes their clocks to run just a tiny bit faster than our clocks on the ground. At the same time, those satellites are moving very fast, around 14,000 kilometers per hour, which causes their clocks to run slightly slower. Engineers must precisely calculate both of these effects, the stretching and slowing of time, or the GPS system would become inaccurate by several miles within a single day. We also see this effect with subatomic particles. Tiny unstable particles called muons are created in the upper atmosphere when cosmic rays hit air molecules. These muons have an extremely short lifespan. They should decay and disappear long before they reach the ground. And yet we detect them on the Earth's surface all the time. Why? Because they travel at nearly the speed of light, their internal clock runs much slower from our perspective. Their 2 microsecond lifespan gets stretched, allowing them to survive the long journey. But this is the crucial distinction. This is a stretching, not a jumping. These satellites and particles are only travelling into the future at a different rate. They are not rewinding the tape. They are not visiting yesterday. Time dilation proves that time is flexible like a piece of rubber, but it has never shown us that you can fold that piece of rubber back onto itself to touch a point in the past. So what are we missing? If time travel is possible, where is the evidence? The most obvious thing we don't see is of course a time traveller. This is the simplest and the most famous argument, sometimes called the Fermi paradox of time travel. If the technology to travel to the past is ever invented, whether it's tomorrow or in a million years, why haven't we already been visited? Surely a future society would send historians, tourists, or scientists back to observe key moments in history. Yet there are no documented, verifiable visitors from the future. There are no advanced technologies left behind in ancient tombs, no unexplainable artifacts, and no credible warnings about future disasters that later came true. But science doesn't just wait for a visitor to knock on the door. We look for more subtle clues. We have powerful telescopes and sensors scanning the universe, listening for any kind of signal. If a future civilization wanted to contact us, they wouldn't need to send a person. They could send a message. They could beam a powerful repeating signal like a sequence of prime numbers or the value of pi into the past aimed directly at our point in space and time. We have never received such a message. The past appears to be read only. We also look for clues at the smallest, most fundamental level of reality. At massive particle accelerators like the Large Hadron Collider LHC, we smash particles together at almost the speed of light. These incredibly violent collisions recreate the extreme energies of the very early universe. In this environment, we can test the most basic rules of physics. One of the most sacred of these rules is causality. The simple, unbreakable law that the cause must always happen before its effect. A glass breaks after it hits the floor. A parent is born before their child. If backward time travel were possible, this fundamental rule could be broken. We might see the effect, a shower of debris particles, fly away from a collision before the cause, the 2 original particles colliding, even happens. In decades of meticulous experiments at the LHC and other accelerators around the world, we have never ever seen a violation of causality. The arrow of time, even at the subatomic level, always points stubbornly in one direction from past to future. Even in the strange and counterintuitive world of quantum mechanics, the silence holds. Some theories once proposed that quantum entanglement, the spooky action at a distance that connects 2 particles, could be used as a loophole to send a message backward in time. Scientists have designed many clever experiments to test this, and every single time the universe finds a way to stop it. information it seems simply cannot be forced to travel faster than light or backward through time. So why is the universe so quiet? If the math of general relativity seems to offer theoretical loopholes like wormholes, why does reality slam the door shut every time we look? There are a few powerful explanations. The first and perhaps most elegant is that it might be forbidden by a deeper, more fundamental law of physics that we just haven't discovered yet. The famous physicist Stephen Hawking was so convinced of this that he proposed an idea he called the chronology protection conjecture. He didn't have a final mathematical proof, but he had a strong intuition. He suggested that the universe must have built-in rules to prevent the paradoxes that time travel would create, like the grandfather paradox. Just as the laws of thermodynamics prevent you from building a perpetual motion machine, Hawking believed some other hidden law prevents history from being rewritten. The universe, he famously said, abhors a time machine and actively conspires to prevent one from ever being built. Another possibility is that the conditions required are simply too extreme to ever exist. The theoretical wormholes that might allow for time travel are not stable. To hold one open long enough for even a single atom to pass through you would need a truly bizarre and hypothetical ingredient, exotic matter. This is material with negative mass or negative energy. While tiny quantum effects can look like negative energy for impossibly short moments, we have no evidence that stable collectible exotic matter can exist in the real world. Without it, any wormhole would collapse into a black hole the instant it formed. The energy required might also be impossibly vast, perhaps more energy than our entire galaxy produces in a year. The universe might allow time travel in theory, but only if you pay a price that is physically impossible to pay. Finally, there's a fascinating idea that the universe self-corrects. What if you did manage to assemble the exotic matter and build a time machine? Some physicists suggest that the very act of trying to create a closed time-like curve, the scientific name for a time loop, would be its own undoing. As your machine powered up and approached the point of being functional, quantum-level feedback loops would amplify. Waves of virtual particles and energy would race through the machine's portal, building up to an infinite intensity. This surge of energy would destroy the machine in a flash of radiation at the precise moment it was about to violate causality. In this view, the universe doesn't even need a specific law to ban time travel. Its own fundamental nature violently prevents the paradox from ever forming, and so the universe remains silent. This lack of evidence is in itself one of the most important pieces of data we have. It tells us that our reality is stable. It tells us that cause and effect are not just suggestions, they are the ironclad rules of our existence. What makes this entire topic so captivating is not the belief that time travel does exist. The true fascination is that the laws of physics as we understand them, the very equations of Einstein, bring us right to the edge of the idea. We can almost see it. We can write the equations for it. It feels almost possible. And yet at the last moment a curtain falls. A physical impossibility, a law of chronology, or the universe's own self-defense mechanism steps in and says no. The most thrilling thing about time travel is not that it is real, but that it almost could be. And so here we are. We have reached the end of our long journey together through the cosmos and through time itself. Think back to where we started. It began with something so simple, so familiar, the tick of a clock. A steady, reliable beat marching forward 1 second after another. It was a comforting idea that time was a single straight line, the same for everyone everywhere. But as we wandered further, that simple clock faded into the background. We stepped out into the universe and found that time is not so simple. We stood at the edge of a black hole and imagined time stretching like taffy, slowing to an almost complete stop. We travelled at the speed of light in our minds, watching centuries pass for the universe in the blink of an eye. We found that time and space are woven together, a single grand fabric that can be warped and curved by planets and stars. We dove deeper into the strange, foggy world of the smallest things, the world of quantum physics. Here the straight line of time dissolved completely. We found particles that seem to exist in multiple places at once that only decide their past when we look at them. We considered the mind-bending idea that our universe might just be one leaf on an infinite branching tree with countless other worlds, other yous, other me's living out every possible choice, every different history. Our journey took us from the comfort of certainty to the profound, humbling mystery of uncertainty. We learned that the universe isn't a simple machine, but a vast unfolding story of possibilities. It's no wonder, is it, that we are so obsessed with this idea of time. Think of how many of our stories, our dreams, and our greatest wishes revolve around it. We dream of time travel, Why, what is that deep human pull we feel? I think it comes from two of the most powerful feelings we have. The first is regret. We look backward into our past and we see moments we wish we could change, a word we wish we hadn't said, a choice we wish we'd made differently, a hand we wish we had held just a little bit longer. That pull to go back to fix, to apologize, to relive a perfect day that is the ache of the past. It's a longing to edit our own story, to smooth out the rough edges of our lives. The second is hope. We look forward into the great unknown fog of the future and we feel a mix of excitement and fear. We want to know what happens. We want to be sure that we will be safe, that our loved ones will be happy, that our dreams will come true. We want to skip ahead to see the end of the book, to find reassurance that everything turns out all right. That is the pull of the future. Regret for the past and hope for the future. We are suspended between these two great forces, and this fascination with mastering time is at its heart a desire to master our own lives, to escape our own human limitations. But after all these grand theories, after all the talk of bent space-time, branching realities and particles that defy logic, where does that leave us? It leaves us here, right now, in this very moment. Regardless of what the most complex laws of physics might allow, regardless of whether the past and future truly exist all at once in some four-dimensional block, our experience, yours and mine, is always and only now. This moment is the only thing we can ever truly touch. The past is a memory, a story we tell ourselves. The future is an idea, a dream we are painting. But the present is real. It is the anchor. It is the solid ground beneath our feet, even as we float through the vast, confusing ocean of the cosmos. And that perhaps is the final comfort. As you rest here, feel the reality of this moment. Feel the gentle weight of your body. Notice the slow, steady rhythm of your own breathing, in and out. This is your clock. This is the only time that truly matters. Time may be a great river flowing endlessly from a source we cannot see to an ocean we cannot comprehend, but you are not struggling against the current. You are not fighting to go backward or scrambling to rush forward. You are simply floating safely and peacefully on its surface. Time may be a great cosmic fabric distorted by suns and worlds, but right now you are just a single quiet point on that fabric at rest in perfect stillness. Time may be a magnificent tree with a trillion branches reaching for the sky, but you are not lost among the leaves. You are resting on your own branch in your own quiet part of the forest, sheltered and calm. The great mysteries of the universe, the secrets of time, of life, of what it all means, they are not problems that need to be solved tonight. They are not a test you have to pass before you can find peace. They are instead a wonder to be held, a story to be marveled at, a grand cosmic lullaby singing you to sleep. Let your mind drift along with that current. Let go of the need to understand it all. Let go of the past. Let go of the future. The universe is holding you. And in this contemplation, in this simple, quiet bit, we find our rest. We find our peace. So sleep well and dream of the stars.